Hey everybody, so my name is Samuel Reed, and today we're going to be discussing quantile regressions in ecology. I'd like everyone to consider a novel. Uh, if you're reading a book and you crack it right open to the middle of the page or middle of the book, there's almost nothing you can gain from reading this section of the book. There's so many different plots and characters and variables, you're really not going to have a clue what's going on. uh, in order to gain actual insight, you need to read the beginning, middle, and end of the book. And sometimes you can just skip the middle as well, but no matter what, you need all of the parts to make the whole. So now I'd like everyone to consider a messy data set, which is, really very common in ecology. And there's really very little you can gain from looking at the least squares of a messy data set. So fitting a line through the middle of it really doesn't do it justice. And in this case, this is a real data set. The dashed line is your least squares regression. And this is kind of similar to opening up a novel to the middle and just starting to read. You're really not going to be able to pick up on all the different variables and plots that are taking hold and playing a role in the overall story. So it's really common that we assume that there's no relation in two variables because we're biased towards this linear regression, when really we're missing the whole picture. It's like we're opening up these novels and just reading them and saying, nope, they're no good, because we started reading from the middle. And quantile regressions allow you to get around this problem. They apply quantiles or they apply regressions at different percentiles. So in this instance, they apply 5 different regressions at the 95th to the 5th percentile. And because of that, you actually find that at the 95th percentile, there's a negative correlation between the ratio of width to depth and the amount of trout per meter of the stream. So you're getting this entirely new ecological result that would have been totally obfuscated by just looking at the linear regression. It would have been totally covered up. Quantile regression basically applies conditional quantile lines to your data. So when I say conditional quantile lines, I basically mean they are regressions that are based on your percentiles. So at your 95th quantile, 95% of the values of y fall below that quantile line. So basically, you are at the 95th percentile, and values of y below it are a part of that. And above that, you would go that there would be about 5% of the data left. So the most simplistic equation that describes quantile regression is this one. And beta is your slope, tau is your conditional quantile, and chi is your independent variable. And quantile regressions allow for nonlinear responses, and it actually eliminates the normality assumptions of linear regression. It actually eliminates almost all of the assumptions of linear regression. So it frees people up, and your predictions are no longer dependent on the mean of your data. So now we're just going to talk about a quick history of quantile regression. So Roger Joseph Boscovich came up with the idea of a regression based on the median in about 1760. And this was basically the germ for quantile regression, because if you were applying a median to your data, that's basically your 50th percentile or quantile. So 200 years later, when people had computers, Roger Kunker and Gilbert Bassett at University of Illinois Urbana-Champaign came up with what we see now as modern quantile regression. And both of these guys were econometricians. So originally, quantile regression was applied to economics and risk analysis. But much of its use in ecology has really occurred in the last 10 to 20 years and was pushed by Brian Cade. So now we're starting to see its use a little bit more in ecology, but it should be noted that quantile regression can be misused, and that's what I'll be talking about later on. So the other big value of quantile regression is that it can point out hidden bias in your ecological data. So any parameter that's not explicitly included in a model basically becomes a part of the error. So these unmeasured variables can influence measured variables, and they could potentially unknowingly bias data. So we may be taking autocorrelated variables and confounding our data. Uh, but your different quantiles actually allow you to see where biases may lie, and you can address them accordingly. It's not a silver bullet, but because you're able to get a better scope of the variability in your data and how it's changing at different percentiles, you're able to potentially see any biases that might exist and look for more relevant variables. Whereas linear regressions, this is not possible. And of course, there's quite a few notable quantile regression packages. And thinking back to Roger Joseph Brockovich, quantile regressions couldn't actually be done without computers, which is what contributed to their late advent in comparison to linear regressions. So QuantReg is the most popular and was actually designed by Roger Conker, who's the man who developed quantile regressions back in 1978. And it's actually very well described in his paper Quantile Regressions in R, a Vignette. But there are other packages like GBM, QuantReg Forest, and QRNN, which contain variations on how to calculate your regression. So you're going to have to pick whichever is just best for you. And then there's packages for MATLAB, SAS, and Mathematica as well. So quantile regressions can be used in a large capacity. It's just a matter of actually knowing when to use them. So quantile regression has been applied to a variety of ecological studies, including plant diversity studies. So Brown and Peat investigated the invasibility of riparian and upland systems at different scales of 0.01 meters squared and 100 meters squared. And quantile distributions were used because the upper limits, so your 90th percentile of data, were more representative than the mean in describing exotic species. And this is because any data points that were less than the 90th percentile were likely in the process of colonization by exotic species due to their dispersal limitations. And they actually found a positive trend in the 90th percentile, where large riparian areas have increased exotics with more natives, and a small positive trend in the median, or 50th percentile, where small riparian areas have increased exotics with more natives. And this could inform management of different riparian areas. And it likely wouldn't have, these results wouldn't have been found if they were just looking at linear regressions. Another conservational study had to do with emergency haying. So haying is a method of feeding cattle in emergency droughts. So it's basically moving cattle onto conservation prairies and letting them feed. Allen et al. Studied how periodic haying can actually be beneficial for prairies since it reduces litter depth. And quantile distribution was used to eliminate the hidden biases where yearly variations in your haying could confound the data. So this study found that with haying, your legumes increase, so your nitrogen fixing plants, whereas noxious weeds decrease. And then finally, we have quantile regression in behavioral ecology. So Chalmers-Jaume and Bloomstein found the method is heavily underused in behavioral ecology. There have been 2 total uses of quantile regression in the journals Animal Behavior, Behavioral Ecology, and behavioral ecology and sociobiology. But it can be a method to account for behavioral variability and plasticity found in populations. So they analyzed your starting distance, which is the initial distance of a threat. So think of the initial distance a human is from a bird, and then flight initiation distance, which is the distance a threat is from the bird before flying. So they found positive trends between both variables, but primarily among larger individuals, so at your 90th, 95th percentile, which provides reason for behavioral ecologists to account for this variability in populations, because if behavioral ecologists are just studying larger individuals, or they're just studying smaller individuals, they're going to get totally different results. As with all statistical techniques, there can be improper usage, and that applies to quantile regression as well. An example of this would be trying to use the quantile regression to prove the humpback model of biomass and species richness in Pierce 2013, where basically intermediate levels of biomass lead to higher species richness. It's a method of explaining why we see so much higher species richness in certain areas. What the researchers did is they assumed that when comparing all of these different ecosystems from multiple data sets, that there was a constraint. So because there was this constraint, because other researchers were only looking at certain site types, such as salt marshes or places that were primarily affected by anthropogenic disturbance, they were missing the whole picture. And by applying quantile regression and looking at all of the different sites and ecosystems combined, you're able to get a fuller picture of what's going on, and this hump-shaped curve appears. But Grace et al. 2012 asserted that really it's largely random variation that's causing the hump-shaped curve that they're seeing. So when the data is transformed into log space, most of the points become clustered together, indicating that it is random variation that's occurring, and most likely not some type of trend that only quantile regression is making apparent. So this would probably be one of the better instances where quantile regression it's not the best statistical technique to apply. So in conclusion, quantile regressions can give new insights about ecological data. I just am left thinking about all the data sets tossed aside and considered unusable when quantile regression might actually tell us something valuable. It may be a suitable alternative to linear regressions, but this means that it should only be used in instances where it is actually applicable. And then finally, we should never forget that correlation does not mean causation. So thank you all very much, and have a wonderful day.